Hello, everyone. Uh, Very glad to be here today. So we're going to talk about vector databases and retrieval today. Most like some try to dig into some specificities. And the idea of this talk is basically to better understand these tools, to better use them. So the popularity of vector search, it really rised since late 2022 when ChatGPT was released, as you can see in the Google Trends. Many tools were released. You have some tools which are dedicated to vector search, some which appeared after 2022, some which were there before that. You also have a classic database like PostgreSQL, which developed some features for vector search, so a very wide ecosystem. A lot of embedding model providers as well. And yeah, as I just said, better understanding these tools will help you to better use them. So just a quick word about myself. I'm an engineering manager and leading the GenAI practice in Theodore Data and AI, which is a service company doing products in data science and data engineering. So I've been working 5 years in the field on various projects like OCR, etc., and more recently, of course, RAG, LLMs, and vector databases. And I've been a speaker at many other conferences. So just with a quick show of hands, who here already built a vector search system, like some retrieval system? Yeah, half of the room. Quite what I expected. So for the other, just reminding very quickly how it works. So for text, for the use case of document retrieval, which is quite famous at the moment, you basically get some of your documents. You get a model, which is an embedding model, which basically creates a representation of your document in a fixed size vector. So it's basically what you have in the middle of any deep learning model. You will add this embedding before doing your classification. And basically, you have a search query. You will use the same embedding model to create a representation of the query. And basically, if the vector representing the search query is close to one of the other vectors, it means they are semantically similar, like the representation is similar. So you can retrieve basically the documents which are likely to answer your query. It works the same for images. So imagine you have like a data set of hundreds of thousands of bridges. You have a model which creates representation of all of these bridges. And when you input a new bridge, you retrieve the most similar one. And to do all this retrieval system, we have in the middle what we call a vector database, which will ease the search. And why should you use a vector database instead of just doing it like manually in S3 or just in a file system? There are several reasons. Just for first, the same reasons as for a classic database. You want to have something like infrastructure separated from the application to ease the update and the querying from users, to separate the load, etc. Because they include many features which will help you search, like metadata filtering, which we can a bit, but also partitioning, hybrid search, etc. And most of all, they allow to benefit from an indexation to search faster. Because when you will have millions of documents, you don't want to compare each new vector to all the vectors one by one. You want to do it a bit more efficiently with an indexing. So they will use an indexing algorithm to improve the search. And there are basically two types of indexing algorithm which are used in most of the recent databases. The inverted file index and hierarchical navigable small words. The first one, inverted file index, it's quite easy to understand. It's basically a clustering. So all the crosses are embeddings. So you can just imagine 2D vectors. And you basically just going to cluster it and compute the centroids of all clusters. So at inference time, when you have a new embedding, you're not going to compare the embeddings to all the embedding in your database, but only to all the centroids, and then compare the embeddings to all the embedding within the cluster of the closest centroid. But sometimes the closest vector may not be there, So what you usually do is that you have this hyperparameter and probe, and you increase it to basically be able to search in a wider range of embeddings to make sure you don't miss the closest one. The second algorithm is, it's not displaying very well. I'm not sure why. It's better. The second algorithm is called HNSW. It's a bit more famous now. And how it works, basically, is that you're going to navigate through a graph. So you start at the top of the graph. You're going to compare your input embedding, your query embedding to an entry point. And then you're going to go to the second one. If the second one, you find out that your query embedding is closer to the second one than the first one, then you're going to stay there and go downstairs. Then you're going to compare to this one and this one. You see that this one is closer, so you go this way, etc., etc. And then you find out this one is the closest one. So you go down, and you keep navigating, comparing every time. So when you have new edges, comparing to all dots of the edges to make sure you're in the closest one, and going to the next step until you find the most similar vector. Is it clear so far? Yeah? Cool. And basically, the main differences between these two indexes is that HNSW, it provides a better quality, which means, of course, since it's an indexing, it's an approximation. So you might not always find the closest vector, but you kind of want it. And but it improves quality, so it improves precision. It's faster as well, but it's worse in terms of memory, which means it will take more RAM. But basically, due to quality and speed, now HNSW is starting to be preferred in most vector databases. And just to finish the general introduction on vector databases, we have a lot of providers, and so this list is not exhaustive. There are many other providers. But you mainly have two kinds of providers: dedicated vector databases, which are basically providers which only do vector search, and general purpose database like Elasticsearch, Postgre, etc., which implements on top of everything they do vector search capabilities. The advantage of using the first type of database is that when you will scale to millions of vectors, they tend to be much faster. And they also will implement a lot of features which are very specific to vector search. Some of them we will see in a bit, which when your vector search project is a bit more complex, you should tend to prefer them. And the other type of database, they are actually good enough for most vector search cases, and they really have the advantage of really simplifying your stack, because you don't need to deploy another system. So now we are going to highlight two projects I worked on, and on vector search. One is about email to duplication, because we talk a lot about NLP recently with RAG, etc. So I'm going to try to put a focus more on something different. But of course, we still have to talk about RAG to see the NLP side. So the second use case will be about RAG. And for these two challenges, we will go through the search challenges, so related to the vector search, and the model challenges, so related to really the algorithm, the embedding model. So starting with the first use case. So basically, the client was an aggregator of real estate adverts. And sometimes you have two adverts of the same property taken by different companies, and they may put a slightly different surface, slightly different price, and slightly different address, because it's not, maybe the address is on two numbers, or it's on a corner, etc. And what they did initially is that they built a huge if machine. So if the price is not too far, and this is not too far, but that, and it kind of exploded, became impossible to maintain. And you know that when the person who built it is going to retire, you have no way to maintain it. So they wanted to build a vector search system to kind of ease this process and improve it. So you have 15 million pictures of different adverts. You put them all in a vector database. And when you have a new advert, you want to compare it to existing ones to see if there is a picture which is very close, which may be from a similar advert. But with this, you still have a lot of metadata, and you want to use them because it would be stupid not to. So you can basically, you basically just want to search in a subset where basically the surface is not too far, the price is not too far, and location is not too far. Because you know that if someone locating an advert in Paris and another one, another company is selling also the same property, it won't be in Madrid or another city. Like it will be very close, and the price will be very close as well. So you can use that to improve the results. So what you want to do for that is basically metadata filtering. It's equivalence of where in SQL. You just say search in all the vector where this condition is met, and this condition, and this condition. And there are two ways to perform this metadata filtering with HNSW. The first one is post-filtering. So let's say you retrieve always a fixed number of vectors of the top 100, and then when you have the top 100, you filter out all the embeddings which don't match your condition. It does not really work here because maybe the good match was the 101st or the 102nd. And so what we want to do here and what works for most use case is pre-filtering. And what you do is that before crawling through the graph, you basically shut down all the embeddings, all the dots which don't match your conditions to only crawl through the dots which match your conditions. But it comes with a performance problem, which is when you drop more than 80 or 90% of the edges, so the edges are the links connecting the dots, the performance starts to be very bad. And of course, in this case, we are always filtering much more than 90% of the dots. So if we used it plainly, like without anything, our performance would have been terrible. So to solve this problem, Qdrant, which is a vector databases, they invented something called metadata indexing. So basically, the founders of Qdrant, they were working on a project similar to Malt before that, where they are trying to match freelances to job offers. And they really needed this pre-filtering feature. They were using Milvus for this project. And so that's where they created Qdrant. And by implementing this new feature, which is called metadata indexing, it's quite simple. It just consists in connecting the dots which have similar metadata. So for instance, embeddings which have a similar price, you connect them so that you know that when you are going to filter out all the other embeddings, the graph will not be as sparse and will still remain quite dense. And so you won't have the performance drop. This is what happens when you filter with one. So it's quite, the performance is always very good and still very fast when you filter with one metadata. But then when you filter with different metadata, it starts becoming a bit more complex, and more complex will applies because you have a certain range of price with a certain range of surface, for instance. And so you don't want to connect all ranges of price to all ranges of surface to all ranges of location, for instance, because then you suffer from the curse of dimensionality and your number of edges explodes. And there is no point anymore using an index because all your dots will be connected. So this is really the key feature we used for this project was metadata filtering. So it just requires indexing. So just before putting your data in, you have an indexing feature in the database you need to use. But I noticed that very often people are not aware it exists, and so forget to use it. So this is my first point. Don't forget to use this indexing. In some database like Pinecone, it's done under the hood, so you don't really control it. It's done for every metadata, for instance, but on most vector databases, you need to do it manually. And now for the model challenges. So the model we use is Dino, which is state-of-the-art for many image retrieval tasks. And basically what Dino does is it combines visual transformer with self-supervised learning. So basically your student and your teacher are visual transformers. And you train them, you train one or the other, I don't remember. No, you train the student. And basically, when you give a picture, you're just going to give a picture and give two different crops of the picture to the student and the teacher. Then make sure they actually get the same embedding, because even though it was different crops, you want them to put the same representation, and which allows you to compute a loss. And then you backpropagate to the student, and the teacher is just an exponential moving average of the student. So this is for the self-supervised, so you don't provide any label. And the model is a vision transformer, and this combination really gives a very good feature and allows a very good performance. So this is an example of a correct match using Dino V2, where here is the query image, and here is a match with a very high similarity score. You see that like the angles are a bit different, but still it's not too hard for a human to see it, but for a model it can be quite complicated. But however, we did not use, the project was quite short, so we did not use any fine-tuning. So we had some problems. So here are some examples of wrong matches we had. The first type of false positives we got was empty rooms, because in a model point of view, the features in both of these images are very similar. So it will put a very high similarity score. Same for these two bathrooms, which are taken with a very similar point of view. And most of our false positives came from bathrooms. Because, you know, like actually bathrooms, they all kind of look the same. The pictures are always very similar. And these two pictures actually look very similar. And even for a human, at first glance, they look similar. Same for this room. At first glance, it looks like the same room, with a different bed. But if you look at it, it's actually different rooms. It's not only the bed that changes. So to overcome that, we are just basically, since an advert contains many images, we use some rules to play around that. But if you really wanted to fix this problem, if this project comes back one day, we will use fine-tuning on hard examples to basically teach the model to what it should not focus on and what it should really focus on. So now we're going to dive similarly into the RAG project and see at the same time the search and model challenges. So this RAG was for an hotel, so a group of hotels with kind of a new way of management where basically in each hotel you have a host and administrator which is in charge of doing everything with no manager. So basically to do their job correctly, they have access to a wide range of sources, and they are basically supposed to find how to onboard themselves, how to, when they were off for like after a shift, what happened after the shift, when there is a big challenge in the hotel, like the elevator is stuck or stuff like this, like always find the right information there. And they kind of struggle with it because it comes from many different sources and it's not very well ordered. So what we do is that we built a RAG. So it's very similar to the search system we just discussed. So at the entry of the search system is just the different sources we just shown. My corner is their internal website. And you just add an LLM at the end. With basically, you put your most similar documents, your query, and you say basically like from these documents, answer my query. The problem we got with the retrieval performance is first that semantically similar does not mean it answers the question. So you may find some documents which are semantically similar, but do not answer the question. Embedding models do not make complex semantic relationships. Unlike, for instance, talking about another use case for a medical company, if in the query it was talking about Doliprane, it would not find any document with paracetamol in it. So not find the embedding model will not find the relation between the the drug and the molecule, while an LLM is much smarter and can do these relationships. You have also a lot of language bias. So if you search in different language, it will prefer the language you're searching on. So the solutions to do that are common methods to improve performance, like chunking, re-ranking, model selection. I don't have a lot of time to go into it, so I just skip it. And the other good solution is that to ease the retrieval stack, you can basically use an LLM, which, as I said, is much smarter. So basically, in this use case, we could just put the query and all the different sources and ask the retrieval system to hopefully find the right document which answer the question. Or what we did is that before putting the question in the retrieval system, we had a little prompt from each of these sources and the description provided. So we provide a description of what all of these sources contain, which one are suitable to answer the question. And so you only get 2 sources. So you can basically, before doing your search, filter out 3 out of 5 sources to make the search much easier. And it improved our retrieval performance from 78% to 89%. So here again, if you want to do that, metadata filtering is key, because you want to have a metadata, which is the name of the source, and be able to filter it. And since we didn't have many documents in this use case, it's the case for many RAGs, so just a few thousands, we actually use the flat index, which is the equivalent of using no index. So that you just compare to all embeddings one by one. Since there are only a few, it's quite fast because thousands of embeddings is considered a few. And so you don't get any filtering problem or precision problem due to indexing. So to conclude, so a vector database are different providers, so mostly the dedicated vector database and the general purpose database. Metadata filtering is often key. So you have 2 types of filtering: pre-filtering, post-filtering. You may need some indexing as well. A lot of different indexes, mostly HNSW, which is the one we use in this project, ANN, and flat index. So sorry, ANN is IVF. And you also have a lot of other features I did not talk about today because we did not use it in this project, but partitioning is often key. So just partitioning your data in different subsystems so that they don't interact with each other to make the search faster and more accurate. You also have quantization. So a lot of vector databases now offer quantization capabilities to basically quantize the embeddings to make the search 4 times faster and the cost 4 times cheaper, and it usually does not hinder the performance. And for the embedding models, be aware of bias. So like the languages, you have many other bias. They are not as smart as LLMs. So try to offshore as much of the intelligent load as you can to the LLM to make the retrieval task as easy as possible. And your task is always slightly different to what the model was trained for if you don't fine-tune. So we saw it for the image retrieval system, and we saw it also for the RAG system where semantically similar does not meet it answer the question. So that's it. Actually, I have some time. So on the left, you have my website with some other talks I did and articles I wrote if you're interested. And on the right, my LinkedIn if you want to discuss afterwards.
Thanks for the talk. I have several questions, but I'll pick only one. I'm curious, when you whether are there methods to when you retrain the embedding, do you have to retrain also the whole index, or are there methods where you can actually update the index rather than? reindex the whole database each time you change the embeddings. Basically.
When you retrain your embedding model, the values that comes out of your embedding model, they will not match. They will not. They will not be similar to the old values. So you cannot compare an embedding you did with the first model and with an embedding you did with the second model because the space will be different. So you have to basically erase all of your old embeddings and create them all again. There is no other solution. So yes, you need to redo the indexing because you will have new embeddings.
So we don't have a new way to retrain embeddings so that the updates, so they're close to the old embeddings.
I'm not aware of any, but there could be if there is a loss of something that tries to calibrate the model towards the same. If you do some calibration in the model and you manage to calibrate it the same way, but I think you will still have some problem because the calibration won't be perfect, so it will cause new errors.
Hi, thanks for the talk. I wanted to ask a question about the metadata filtering in the HNSW graph. Does the computation of the slightly altered version of the nodes and links happens at inference or at indexing? And if so, does it affect memory usage and how?
It happens at indexing. Okay. Because you don't want to redo this computation all the time because it will be the same every time. And yes, it does impact the memory, which is why, as I said, you don't want to put too many. And but I won't be able to give you a ratio.
Okay. Thanks for the talk. About the metadata filtering, I was wondering, did somebody try to encode the actual metadata as embeddings, or like to make a new vector that combines both the photos and the metadata encoded in some way as an additional features?
So you will need a multimodal model. So you could do it, but it's something that happens quite often with text. For instance, it's easier with text because you can just put your metadata within your chunk that you can embed. But the thing is that it's not you don't have a guarantee that you will get if you just encode it, you don't have a guarantee you always get something with this metadata. While with filtering, it's something where you have a guarantee, so it's just more accurate.
Thank you. We had a talk yesterday on doing RAG with a graph database, and I was wondering when you have like pre-complex relationship, so the metadata is just not flat. Is there a way to combine in this vector database? I mean, are you aware of any vector database where you can combine advanced relationship filtering, kind of a graph-ish type of filtering?
I'm not sure I understood the question very well. But basically, if the metadata is not flat, one way you could think of is trying to make it flat with an LLM. But it will cost a lot in inference, trying to infer all your documents within an LLM and asking for a structured output to make sure you get one of these 10 fields, for instance. And then you can index your data with this new metadata you just computed. But it's quite costly. But yeah, no, otherwise I don't know any. Not sure. I'm not sure I understand the rest of the question.
Okay, thank you for the talk. I have a question. I mean, you were saying that for the graph data, the vector search is not as good as an LLM. But this is because I wonder if it's because you are using small vectors and small models. What if you were using an LLM to actually get the vectors and then you store the big LLM vector in your database? How would it perform? And would you avoid this to having to first call an LLM, then to have this two-step stage if you use the LLM directly for the embedding?
That's a good question. Maybe if we used actually an LLM for the vector search, it will work better probably, but to be much more costly.
Because you are hosting the model yourself, or your query on API?
No, it's OpenAI.
So it's more costly definitely, but still okay.
Yeah, but with OpenAI you cannot use the LLMs for vector search. But I mean, if you had an open source LLM, you could just remove the last layers to get an embedding. Maybe, but just by default, the way it's trained, you're just basically encoding something and encoding something else and trying to match it. So the best thing you could do is find something semantically similar. So while with an LLM you can actually ask a question and ask, does it answer the question, or you can actually ask a task, like define a task. With vector search, you can only search for similarities. So by default, you want.
Okay, thank you.
Thank you very much. It works? Okay. Thank you very much for the talk. I'm actually curious how to choose a vector database that will go to production with your project later. Because we have a lot of marketing resources devoted to vector DBs these days, but it's really unclear which one will work best.
So self-promotion, you will find here a talk on how to choose a vector database. But basically, there is no such thing as the best vector database. It really depends on your use case. So as I said, if you only have a few thousand of vectors and you don't have any complexities, use a system already in place. I tend to use Qdrant a lot for my projects because they have a very good DevX and a lot of features. Mostly you can use it on disk. So just as a file, so it's very good to interact with pipelines. I use something called DVC, I don't know if you know it, but it basically stores version of files, so you can just basically store version of the database when you iterate on it, and it's the same client then to go to production. Their managed service is very good, and if you have just, let's say, 100 or 200,000 of vectors, you can host it for free. So overall, and they are the one who invented the metadata filtering, so I know they do it well. I know they have a very good engineering team, so I tend to use this one, but other ones can be very good as well.
Okay, let's thank our speakers again.